In the first part of this lesson, we talked about interpolation and extrapolation, but something I glossed over and didn't talk about were independent variable and dependent variable. These are terms we've talked about in grade 9. Our independent variable is the variable that predicts the outcome of the other variable. It's the one that we set a value to and then use its value to predict the value of the other variable. So it's like the x. It's the first value in your table of values. It's the first column or first variable in your table of values. It's also the one that we graph on the x-axis. So if you want, beside this, you can even just put an x to remind yourself very quickly that that's really the x that we're talking about with that. In contrast, the dependent variables like the y, it's the variable whose value depends on the value of the independent variable. So perimeter depended on the side length. Side length was independent. It's the second variable in your table of values, and it's graphed on the vertical or the y-axis when we graph that. I also mentioned interpolation is using your line or curve of best fit to predict values between or within known data points, and extrapolation is using your line or curve of best fit to predict values beyond, which is before or after known data values. So if you can take some time and write these definitions down, just put the video on pause and do that. Further to that, there are two examples here that I would like you to try doing, creating a graph for, and we might try submitting that just as an experiment to make sure we know how to submit some work. So I'll give you a chance, put the video on pause, you can try, get the definitions copied down, and then a couple of graphs here with these two examples. Further to that, after you're finished that, so flipping back, I'm going to go back to page. You'll notice that there are some questions where I've given you some graphs and you're just reading values off of that. I'd like you to try those as well. Example 1 and 2, I've given you the graphs for them, so you can answer those. And 3 here, as far as your maximum height of the soccer ball, it should have been about 62.5 meters there. So you can put that or check your answer. Your maximum height is on this axis, and it reaches a tall point right here, which is about 62.5 meters. 62.5 meters. How far down the field was the ball when it reached the maximum height? So if we look at this value right here, that looks like it's 25 meters. And then how far down the field was the ball when it landed? So that horizontal distance down the field, its height would be 0 when it lands. So I'm looking at this, which is known as a 0 or an x-intercept, and that gives us 50 meters down the field. There. And how high did the rocket go? Well, if we look at this, it's just below the 250. It's close. So any answer between 245 and 250 I think would be sufficient for an answer. Definitely not 250, but so like 245, anywhere between 245 and 249 I'd be happy with. So I'm going to put 247 here. Just a happy medium on that. And when did that happen? So following that height down, it's happening at a time of 7 seconds. And then how long is the rocket in the air? So the rocket was shot from the ground. The height was 0 at time 0, and it reached the ground over here at 14 seconds according to this model. All right, taken. Example number 3 is one that you're going to actually put the equation into Desmos. So make sure you know how to use Desmos. Put that in. Instead of H, you can just use the letter Y, and instead of T, you could use the letter X. If you're not sure how Desmos works, then that would be a good thing to get in touch with me or one of your peers to see if they can help you through working with Desmos, which is a web app. Like a website, or you can download it as an app to one of your devices if you would like. So I'll give you some time, or you can have some time right now to do that. Just put the video on pause, and then you can check your work after the fact. Okay, I'm going to experiment with this and see if this will work this time. Last example here, if you describe your relationship between height and time, it is a U-shaped curve again. You'll notice that these two examples above are U-shaped curves. It's a U-shaped curve. The ball first increases in height to a maximum and then decreases again. So something to that effect would work for that. Okay, so I've got that written in there. The ball first increases in height to a maximum and then decreases again. It's a non-linear U-shaped curve. So our maximum height, when we put this into Desmos, you should be able to tap right on that maximum spot, and a second tap will give you the actual coordinates there. And when I did that, I got a 12.98 meters approximately. So 12.98 meters, and I think I have the highlighter on instead of the actual writing tool, but that's okay. You can still read that. How many seconds after the ball was thrown does it reach the maximum height? So that's looking for the x coordinate, or the t coordinate in this case. So that should be 1.531 seconds, depending on how many decimal places your Desmos is going to. How can you tell that the initial height of the ball, the height the ball is thrown from, is 1.5 meters from the graph? So from the graph, the spot you're looking for is you're looking for the y-intercept. Okay, and you should be able to, again, tap on that spot, and it's going to pop up with that y-intercept. It's the place where t equals 0. Okay, you want the initial value, the initial height, the height when time equals 0. The place where t equals 0. All right, it's our y-intercept. After how many seconds does that ball reach the ground? Again, you're looking for a 0 to the function. Where is the height 0? And that height is 0 at a negative value, which doesn't make sense, but also at the positive value of 3.158 seconds. So after or at 3.1858 seconds, the ball hits the ground. Okay, so hopefully that works out for your answers for that. Okay, example number 4, the cost of operating a concrete cutting machine is modeled by this equation, where n is the number of minutes the machine is in use. Again, use Desmos to graph this relationship and answer the questions. And remember, when you do that in Desmos, you can use replace the c with just y and replace the n with x. And then when you have your x and y coordinates, the x would be the n, the number of minutes, and the c is the y. The y would be your cost. So put that into Desmos, put this on pause, try it out, answer the question, and then we'll talk about the next part of the graphs being U-shaped curves. Okay, if you put that in Desmos, you would have found that the lowest point on this curve is at 15,170. So the 15 is your n. It's the number of minutes that the machine should be in use, and your c is the cost. So if how long must the machine be in use for the operating cost to be a minimum? The machine must be in use for 15 minutes to have a minimum cost, and the minimum cost would be the 170 there. Okay, so I have my statements in there, my sentences to talk about those. So all of these examples have graphs that are U-shaped. They're these nice U-shaped curves, and these U-shaped curves are called parabolas. So these are U-shaped curves, and these graphs are called parabolas. P-A-R-A-B-O-L-A-S. Parabolas. Parabola or parabolas. The algebra model that represents them are quadratic relationships. Okay, so these are the quadratics that everybody's been talking about, quadratic relations. So no longer will we be working just with straight lines. We now have these lovely U-shaped curves. So your job now is to finish the rest of this. Okay, so you're going to use your Desmos technology to graph these relationships. I don't suggest putting them all on Desmos at once. I would do them maybe one at a time. Underline the relationships that are linear. So when you graph it, does it give you a line? Circle the ones that are U-shaped, quadratic, and if it's neither, put an X through it. And you'll get a chance to check this in a document. Also, examine the equations that were quadratic in this example and what makes them different from other equations. What do you think it is in the equation that tells you the relationship is going to be quadratic? We know that linear relationships have certain patterns to their equations. Quadratics also have patterns to theirs. So again, try and make a conjecture there. Example 7, use technology again to graph them, classify them as opening up, which is smiley, or opening down, which is your frown. If it's a frown, it opens down. If you're up and you're happy, you're smiling. It's an opening up. Example 8, compare the equations for the quadratics that open up with the ones that open down. See if you can come up with a way to determine which way the quadratic will open from its equation. So a bunch of conjectures to make here, and if they're wrong, it's not a big deal. We'll fix it up later, but see if you can figure those things out. Good luck!